Hello, everybody. Good morning. Thank you very much for coming. It's early, I know, but we have a lot to go through, and I'm going to be very quick with my introduction, and then Michelle will introduce Dr. Roesler, who is our keynote speaker today. Just a quick, I jotted down some of the numbers for you guys to see how the workshop is growing. I don't have very early year numbers, but I do have some numbers for last 4 or 5 years. And because early 1 or 2 years, nobody knew where it is going to go. So we didn't keep any numbers. So, but before I get to those, quick logistics for anybody who is new here, who didn't come here yesterday. The workshop is open to everybody. We do not care we do want actually students to come in. We don't want just the practitioners and those who are wanting to get into the profession. We do want them to come in. And it doesn't matter what nationality they are from. It just there is a request that any foreign national or even US citizens with foreign organizations should register with the registration desk. And that's about it. There is a shuttle provided from Homewood Suites to here at 7:30 a.m. and it goes back and forth. It's very short distance. There is a shuttle provided from here to Homewood at the end of the workshop and on Wednesday dinner. There is parking reserved for attendees only. The restrooms are across the lobby. Please do not exit from that back door there. That goes into some sort of reserved area, so please don't go through that. Just use this front door that you see here right next to the clock. Any questions, feel free to come and ask me or the front desk. Thank you very much. Let's get to, I'm going to start with thanking the sponsors, because without them, we just couldn't give you all kind of support. The food and the dinner, all sorts of things that we have purchased, they are only possible because of the sponsors. And also obviously thanks to all of you for coming here and presenting. And there is a larger community which is actually right now they might be listening on the YouTube live stream. Yesterday there were about 22 present. At one time, there were 22 people who were listening into it. Today, there might be more. This is the history of the workshop that I could cobble together. It started in 2007. You can see number of talks have increased a lot. They jumped up a lot when CFS Community Day was added, clearly around 2015. And that shows you also a clear jump into the user community that we access. We are not advertising this workshop anywhere. It's just word of mouth and people in the spacecraft community, flight software community, those who know, they come here. The presentations are not weighted like IEEE conferences or anything. These are just simple but very important ones, and you get to meet a lot of people here. Number of our sponsors is increasing, and I can see that the number of people attending in person is clearly increasing every year. So thank you very much. How do we manage this? We have a lot of administrative support that we take from the hosting organization. Rhonda and Terry, the ones you saw outside, there is a lot of support from the AV folks and also from accounting. A lot of volunteers make this happen. We meet almost like bi-weekly for 5 months. And then from call of presentation to the last day. And then we also meet once a month throughout the year. Anybody among you is welcome to join, especially those who want to host the workshop in upcoming years. Anybody from those organizations, they're welcome to join this. We do have a constant contact, and I request you guys to put that under, make sure it is not filtered out by your spam filters. And we are now using the Gmail to contact you. That and constant contact. Those are the two main ways we contact you. We take just about $2,500 from the sponsors, and our expenses are the ones that I have listed. Accounting is kept by GHU APL. In future, any questions you have, please send those to that email, or just even Space FSW email, and we'll be good to, we'll take those into account. If you would like to volunteer, or if you think that number of days should be increased, or whatever your suggestions are, feel free to send those. That's it from me. I'm going to hand over to Michelle. We are running a little bit behind, but I think that's okay. Thank you. I need to set up his presentation.
Oh, okay.
So I'll just set that.
So I'm going to stand next to you.
Yes.
So I have the honor of introducing our keynote speaker. Dr. Gordon Roesler is a retired Navy captain, and he has a bachelor's in physics from the Naval Academy, and then he went to MIT to, I'm trying to figure out.
You can speak in English. Sorry.
That's what I was trying to speak into.
Okay, good.
And then he got his PhD at MIT in physics. I'm going to just share snippets of his career with you, and you could really see his research passions as I share these with you. So in 2002, he was a program manager at DARPA, where he originated the spacecraft for universal modification of orbits called SUMO, and the front-end robotics enabling near-term demonstration called FRIEND. After being a DARPA program manager, he worked as a physicist in the Ocean Sciences Division at SAIC, where he proposed and managed a research program for a revolutionary wave-aware control system for small manned and unmanned boats. In 2009, he was the director of energy informatics at USC, where he started new programs in the application of computer science to energy systems. In 2012, he was the senior project engineer at the Australian Centre for Space Engineering Research at the University of South Wales, defining a program for a spacecraft to monitor Australia's natural resources. So you could see that his love of the ocean has been a huge impact on where he's been. Now in 2014, he returned to DARPA in the Tactical Technology Office, and he is the program manager for the robotic servicing of geosynchronous satellites. So I'm really excited to introduce him, and he will talk about the RSGS program today.
Thank you. Good morning. Can you hear me? Okay. I can't tell from here. Oops. Let's put this in the project mode here.
I think that is not going into the...
Okay.
Yeah, see, this goes into this mode. Okay, but it's not it's not doing that on the YouTube.
Well, I'm sorry to hear that.
That's okay.
What do you want to do? Do you want to go to a different mode?
That's what I'm trying to figure out.
This is fine. Can everyone see that?
Yeah.
Let's just
Go through this?
is fine.
Okay.
So as Michelle said, I'm at DARPA, and I am the program manager for a program called Robotic Servicing of Geosynchronous Satellites. But what I really want to do today is to get you to think more generally about robotic operations in Earth orbit and where it leads and what it means for the future of space operations.
Give me 1 second.
Okay. I've been there for 3 years. The slides that we're using today, I presented recently at International Communications Satellite Conference in Trieste, lovely city if you haven't been there, talking to the people basically who design the payloads that go on the commercial communications satellites where your DirecTV and your Sirius radio and that sort of thing come from. And I'll explain why DARPA, a defense organization, is involved with the commercial business. Hopefully that'll become clear. But Oh, and I should give you a disclaimer at the beginning. I know very, very little about flight software. I consider myself the cheerleader for this program as much as anything. If I show them they're violating Newton's laws or some other physicsy-like thing, they listen to me, but otherwise I try to leave them alone. How are we doing? Are we okay on this now? So, with that as a background, this is what we're trying to do. There is nowhere on Earth where we spend $1 billion on a system and then never inspect it and never maintain it and never upgrade it. I mean, that's crazy, right? But that's what we do in space. So the idea of this program is let's do those things for those $1 billion assets that are out there. The commercial ones are a mere $300 million or so. The military ones can actually be over $1 billion each. So let's be able to inspect them. Let's be able to repair them. Let's be able to upgrade them. Our commercial partner, which we have, and I'll explain what that means in a little bit, is even adding a refueling capability to our robotic servicing satellite to be able to increase the life of a satellite that's still working fine, it's just running out of gas. We'll be able to repair a couple of easy things like solar panels that are stuck. We have cameras on the end of our robotic arms, so we'll be able to get within inches of mechanisms that have failed or something that we don't understand on the outside of a satellite. And we'll even be able to attach things. Now today, none of those satellites that are up there have USB ports on them, sadly. So when we attach something, it will have to have its own power and its own communication system. But there are still numerous advantages to attaching things today to the outsides of our spacecraft. There's new opportunities for businesses, new opportunities for science. So we're going to enable all those kind of things. What is DARPA's role in this? Well, it's what it always is. We overcome the technical barriers. We, in this case, are doing something that goes beyond a demo. Often what DARPA will do is we'll do something and demonstrate a technology to a certain level, and then we'll say, let's say to the military, do you want this or don't you? An example of that was the stealth program in the late 1970s and early 1980s. DARPA built a technology demonstrator for stealth. It was called Have Blue. If you looked at it, you'd think it was an F-117, but it's really 80% scale. And then the military took that over and invested in the actual production line. This program's a little bit different. Our satellite is going to last between 8 and 15 years. It's going to have enough propellant on it to do dozens of servicing missions because we want to change the way space is done. And we didn't think that a single demonstration would do that. As a matter of fact, we have some objective evidence that says it won't do that. As many of you know, the design community for satellites is very conservative. So we thought that by staying on orbit for several years and doing dozens of missions, that the design community would start saying, oh, okay, this actually works. It's safe, it's reliable, it's useful. So how can we design our satellites to take more advantage of it? And that's what I mean by develop years of operational experience and data and sustain the capability. We also want the entire world to understand what we're doing and what the possibilities of this technology are. So we'll be reporting our position to the Space Data Association. We'll be sending down real-time video. I'm hoping to have the Discovery Channel work on this someday. So that's really what my program is all about. But I'm going to try to be more general and talk about, how should our imaginations work with this? So we are going to geosynchronous orbit, and people in the scientific community don't think much about this orbit, but they asked Willie Sutton, the bank robber, why did he rob banks? And he said, well, that's where the money is. Well, geo is where the money is, folks. So here's a table of the revenues. In other words, the value of the bits that went up to geo and back by year. Last year it was $127 billion. Now compare that to the budget of any organization you want to think about. NASA, $19 billion. Certainly DARPA, $3 billion, right? That's a lot of money. And the reason is because of that persistence, right? So So here's your DirecTV antenna on your house, and it doesn't have to steer, right? That has economic value. That has enormous economic value. So there's over 300 commercial satellites in this orbit. And so now I get to explaining why DARPA chose to partner with industry to do this. Because there's 50 or 60 government satellites in this orbit, but over 300. So we said, well, if this satellite that we're spending a lot of money on to build can service those commercial satellites as well as the government ones, we'll get more opportunities to get data. We'll see it operate 5 times as often as if it was only servicing the government ones. So we entered into this partnership with industry in order to do this. And by the way, if the government needs to use it, we can write them a check, right? So the idea, the kind of program idea is to get national security value from the satellite. I mean, that is the D in DARPA's defense, right? But by providing this thing and making it self-sustaining, because it'll make money for the owner by servicing these 300 commercial satellites, we'll get the data. We'll understand how it works. We'll get the lessons learned, what it can do, what its limitations are, and that sort of thing. It'll be available. So it's kind of a win-win, both for the government and for industry. Great. So this year, the news from Geo wasn't all that good. These are 4 news articles on failures. So you saw the 300 birds or so up there. What that means, given their lifetime, is that every year, oh dear, did I do that? Well, so every year we send 15 or 20 satellites out there. When I say we, it's mostly industry. The government sends 1 or 2. Industry sends somewhere between 15 and 20. And then 15 or 20 are thrown away because they've run out of propellant or something's broken. These are broken ones. Most of these were quite old, 14 years old, 19 years old, 20 years old, 18 years old. Those are well beyond, except that 14-year-old guy, well beyond their design lives, which is typically 14 to 15 years. Nevertheless, it would be nice to be able to do something about this, to be able to go up and look at it and say, well, what went wrong? You know, a large cloud of debris came from this satellite, and then they lost contact. It's interesting that there's a company, ExoAnalytic, that's actually making money by just imaging satellites. The operators buy these images, the government buys these images, and they happen to be looking at this thing when there was a big puff, and then the satellite went offline. So we would like to try to deal with these mysteries. We'd like to get a little bit more information and maybe do something about them in the future. So these are our notions. Today, first of all, whatever you're going to send up has to fit inside a fairing, one fairing, right? The sort of poster child for this is the James Webb Space Telescope, which is really folded up. Has 126 deployment mechanisms or something like that. So that's a tough constraint. I mean, that's been very difficult, very challenging for the engineers in order to get all those deployments right and that sort of thing. Also, as I've been harping on, there's really nothing you can do about failures out there today. And you can't upgrade your software. You can upgrade your software, yes, okay. But if you want to put on a new antenna, add a new processor, a new sensor or something like that, that is not something that we can do today, and we want to change those things. So we want to enable on-orbit upgrades, on-orbit servicing, and even in the longer term, on-orbit assembly. I will tell you that my spacecraft does not have in its requirement set any assembly beyond attaching modules to operating spacecraft, but if you look at the robotic arms, and we'll talk about this in a little bit, you'll see, you can imagine that they have capability to assemble things.
That didn't work?
It always works, right? Garbage in, garbage out, I guess. I don't have it memorized, so I'm kind of at a loss here. Don't know what the
Sorry.
next slide is.
Can you get me back in? It said hide, and then it just killed me.
Well, first,
So tell me to hide.
I recognize that.
There it is.
My wife actually works for Microsoft. She has a really interesting job. Makes a lot more money than I do, that's for sure.
Once you go Mac, you never go back.
yeah, that's no, we want it to unextend.
That's adequate but not optimum.
Here, let me-
So, when I was, I'll ad lib here for a little bit. When I was preparing this program, and as Michelle mentioned in my biography, I started the work at DARPA on robotic servicing of unprepared spacecraft back 15 years ago. And then I came back to DARPA in 2014. And the director of DARPA understood why I wanted to do servicing. She says, I get that. I understand the capabilities you're bringing. And I understand that the revenues will help to make it sustainable, that this commercial company will be able to do that. And she said, but I'm interested in more than servicing. She said, I'm interested in transformation. I want to see everything change. I want to see modular satellites. I want to see huge things being built in GEO and that sort of thing. And so we kind of have these two goals. We want to establish this persistent servicing capability, but we want the design community to look at this and say, okay, how can we take advantages? That's the transformation that I'm talking about. How can we take advantage of highly dexterous robotic capabilities in space? We're DARPA, we have to have a graph. This graph was prepared by Dr. Brooks Sullivan of Sullivan Analytical Technical Services. I think that's what he calls himself. He works with me. He's my CTO, as I say. And he thought about these different things that robotics should be able to do in terms of two figures of merit. One of them is value, which may not simply be monetary value. It may be something else, but some kind of value. And how complex is it? So you can see that these are highly qualitative. Nevertheless, one of the easiest things to do is just to go inspect a spacecraft. Now, the closer you get to it, the more challenging that becomes from a safety point of view. But there is a certain value associated with inspection. As a matter of fact, there are companies working on satellites, and the Air Force has a couple up there now, that their only job is to do inspection of objects in GEO. The Air Force's ones are called GSAP, which is a long acronym, but it's geosynchronous imaging. There are commercial companies that are looking to do this as well, just inspection. A little bit, at the other end of the scale on very hard and technical complexity is to go inside a spacecraft and pull a box out and put another one in. I mean, that's very, very difficult. We do not propose to do that. Assembly, it's interesting. So repair. Studies have shown that some of the stuck solar panels and stuck antennas that happen at the beginning of life when you're first deploying an antenna, and that happens about once every 2 years to a GEO spacecraft, as it turns out. Studies have shown that sometimes it takes less than a pound of force in order to fix those. Just there's nothing there to apply that force today, right? Sorry? They try. I mean, they do all this stuff: jiggle, spin, thermal baking, all these kind of things. Sometimes it works. More difficult repair jobs would have to do with, actually moving things around, like a harness tangled something, or some MLI came loose. You got to stick it down. So there's a spectrum of what's involved in repairing a satellite that's already on orbit. And why do I say that assembly is actually somewhat less technically complex qualitatively? It's because you have design control over both sides of the interface. You got to choose what the things were to go together, whereas in the repair case, you don't have that option. You have to deal with what you find when you get up there. So it does add a little bit of complexity. Today, replenishment is fairly technically complex because they're not designed to be replenished. So here are the steps in refueling a legacy spacecraft today. Peel an insulation back, cut a lock wire, take off what's called a B nut, put on a safety valve in case you can't get the original valve shut, open the original valve, transfer the propellant, shut the valve, shut the safety valve, and replace the insulation, okay? So that's kind of a pain. On the other hand, the value is cosmic. It's a very valuable thing to do. If we start designing future spacecraft, so future is sort of in blue here, if we start designing them with quick disconnects, the difficult becomes easy. It's a one-step process, right? Just put the probe in, transfer propellant, and you're done. NASA Goddard has already designed that quick disconnect. It's triple sealed. One of the nice things about it is it's got a label on it. So you're not going to put the oxidizer in the fuel tank or vice versa. The ones today don't have labels because they're done on the ground. What do you need a label for, right? Who's going to go and look at it once it's on orbit? But we're going to be doing that. We're actually going to be doing this refueling. Relocation is sort of the first cousin of refueling. So instead of putting propellant into a spacecraft, we can dock with it and push it to a new orbit. The first program that I started at DARPA back in 2002 was called SUMO, Spacecraft for the Universal Modification of Orbits. In other words, it was a space tug. And I did not choose the acronym because my last name is pronounced Roesler. That is a fallacy. That did not happen. But it is a high-value activity, and it's a lot easier than refueling. So my guess is that once we get up there, some operations are going to be done with refueling and some are going to be done with relocation. The highest value, though, I'll tell you, is if you send up, let's say, a commercial satellite, $300 million plus the launch cost plus the insurance, and a solar panel doesn't come out, or God knows, $1 billion military satellite, the value of that operation is amazing. And the insurance companies are interested, right? As a matter of fact, someday these spacecraft are going to be like the insurance adjuster. The insurance company will not pay you for damage to your car until they come look at it, right? So today, insurance companies pay for anomalies on orbit without getting a chance to look at them and see what's going on. So this is the opportunity space that we're working in. This is a pretty good image of the satellite that we're building today, RSGS. We're putting this dexterous capability up there, as I said, for two different reasons. One of them is to provide that resilience, those services to today's spacecraft, but also to motivate the design community to change the way they do things. Public-private partnership, I hope I've explained the reason that we decided to partner with industry on this is that there's many more opportunities with commercial satellites for servicing than there are just government ones. The revenues that they get from doing those servicing will sustain the capability. It does save the taxpayer money, indeed. And our partner is SSL in Palo Alto, California, the world's leading supplier of geospacecraft. So this is their bus. This is their 1300 bus. And this is the government-developed robotics payload on the end of it, in not quite its current form, but pretty close. These two arms, the only, let's see, an unrealistic thing is that these arms are shown without the insulation on top of them. You can see the details of the joints in these pictures, but these would actually be covered by insulation. Thermal control of things in space is pretty interesting. So that's my program. And these are the things we propose to do. The inspection that I mentioned, pushing on solar arrays and that sort of thing. Here's the space tug mission, and finally installing things just mechanically, because again, no USB port, just mechanical installation on operating spacecraft, both commercial and military. And our partner, SSL, is adding a refueling capability to complement these missions. So once again, things continue to go wrong despite the investments we make in reliability and mission assurance and that sort of thing. Here's a military and a commercial example. In the case of the first advanced CHF satellite, it experienced a propulsion anomaly on the way to GEO. They were able to use their attitude control propellant in order to get it the rest of the way up, but of course that kind of limits your life because you've got all this primary propellant that you can't use and not enough ACS for its full lifetime. So maybe someday that could benefit from a space tug to come along and bring it back to the stationary slot in GEO as its propellant is exhausted. And then here's a commercial satellite, New Dawn, that had an antenna deployment anomaly. So the antennas, the reflectors are folded up here on the sides of the satellite, and one of them didn't unfold properly. Continues to happen. So we've been working on this for a long time. And of course, all my pictures are hardware, software. Sorry, guys, I don't have any software pictures except, well, here's a rack, right? We've got a rack. And we will talk a little bit about what it is that we're expecting out of our software and why. There's a lot more than a traditional, let's say, a scientific mission or something like that, and I'll explain why in a bit. We started asking the question in the laboratory, is it possible for a spacecraft to detect another spacecraft, range it, find its pose, come in and dock with it, all without commanding from the ground? There have been other missions that have done autonomous rendezvous and that sort of thing, but we wanted to go all the way into a docked condition with the robotic arm. So that program, that SUMO program, was a laboratory-only program. By the way, all of the robotics work that's being done here is being done at the Naval Research Lab down in DC. They're not the manufacturers of all the hardware. They're subcontractors that are doing that stuff, but they are the integrators. They're the brain trust, and certainly all the software is being done there. So in the laboratory at NRL, there is a facility, and let me see, you said 50 minutes, yes, okay, where two spacecraft can be simulated to move with respect to each other, all 12 degrees of freedom that are involved in that, and we could test it with realistic flight-like software, flight-like sensors, realistic orbit dynamics, and so we showed in 2005 that we could start at, say, 15 meters away and drive into zero, find the docking point that a human had selected, and go in and dock with it, all with no operator input. And the way I knew that was all the controllers, when the demonstration started, they stood up and they walked away from their monitors and they just stood up and looked. That's how I knew it was autonomous. We do, however, we do intend to enable teleoperation of the robotics as well. And that is a workstation that can be done from. So, automation versus teleoperation. When two spacecraft are in very close proximity, and you're dealing with the time delays of going to GEO, right? So the speed of light time delay is only about a quarter of a second. But when you add in network delays and compression and encryption and that sort of thing, the time delays can run up to several seconds. So in this dynamic situation, it's not safe to try to teleoperate that operation where one spacecraft reaches out to grab another. So that part of our robotic operation is automated. And I will show you the stack of software that we use to do that in a little while. But once we've done that, there's this wide variety of things that we might want to do. Anomaly correction, like pushing on a solar panel, is one of them. It's very difficult to automate that because you don't know a priori what the configuration is, and therefore what your machine vision should be looking for. So once we have docked, once we have reached out, grabbed that customer satellite, and then rigidized the arm by setting the brakes on all of the joints, now we have a static situation instead of a dynamic situation. So now teleoperation, those time delays become annoying, but they're not unsafe. So that's the difference. We automate the dynamic operation and we teleoperate just for timeliness, efficiency. We teleoperate some of the other operations. Um, so, so we have done, there's a lot of hardware-y stuff that's gone on, but the software has been in development to do this since 2002. We keep improving and adding to it and that sort of thing. We've developed a lot of tools to go on the end of the arms to give us a lot of variety. This little upside-down Mickey Mouse looking thing at the bottom is a tool changer. So you can take one tool off of the robotic arm and put another one on. That gives us a lot of flexibility. We've tested these arms for all the things you want to test them for in space. Launch environment, vibration testing, EMI, thermal vacuum. And then we've done some integrated tests. So here's an engineering development arm with a simulated satellite deck with a bunch of tools on it. Here are actual qualified flight controllers using NRL's Neptune flight control system in order to control this as though it were in flight. So that's going on very well. Okay, here's the one slide you'll care about. I've mentioned that we want to do an automated docking for safety. So we've implemented in this stack of software what I call robot reflexes. We want the arm to reach out and find the point that it's going to dock with. So that's where we have in the upper right-hand corner feature tracking, right? And different features have to have custom algorithms to identify them. So a circle, which may be the representation of a bolt hole. Some satellites are actually bolted onto their launch vehicles. Or a Marmon ring, which is a large aluminum ring that is duplicated spacecraft and booster, and then they're strapped together. Or something that someone's actually put up there intentionally. So we want to be able to recognize those with the feature tracking. We want real-time pose and range determination as we move in. We're using a LiDAR. We try to do this with stereo video and structured light. And the problem with that is sunlight. It goofs it all up. LiDAR is much more robust to sun angle and that sort of thing. But we also, these reflexes are an automated response to something going wrong. Specifically, motion of that client satellite that wasn't anticipated. Right? We can tolerate a certain amount of motion, but if it exceeds that, and we didn't plan on it, we want that arm to come back, just like you're touching a hot stove. We want that to come back without the operator having to think about it, and we want it to come back on a path that is guaranteed free of collision. So we have an obstacle avoidance. I mean, that operates going in, but it also operates coming out. So we have an automated abort feature built in. And then our FDIR, fault detection and response, includes, but is not limited to, looking for unanticipated motions of the client. So you're familiar with the servo control, I'm sure, of any sort of thing, and it's no different for robotics, except there are 7 joints, so you have to figure out how to move the joints to get where you want to go. But we also want the touch to be soft. We don't want to bump into our client because we will send it in a place where we didn't want it to go, or will create damage. So there's, some of you may be familiar with the notion of compliance control, where there's a force torque sensor on the end of the arm, and that feeds back into compliance control and allows the touch to actually be soft. That's extremely important for safety. Okay. I was actually, during some of the sumo demonstrations, they actually let me go down and move the model of the client satellite and watch the arm pull back all by itself. That's very reassuring when you do that. So the bus, the satellite bus, is being provided by our commercial partner. Oh, and by the way, I've only shown the robotic arm control system. I haven't shown the entirety of the robotic payload software stack, unfortunately. Actually, that's kind of ITAR, so that's not here. But this is pretty straightforward. But that payload has to talk to the bus. And the bus is going to be responsible for the usual, navigational kind of stuff, and including RPO. The RPO function of the satellite is being done by Draper Labs, many of you may be familiar with. So we have to figure out how these two things talk to each other and who's responsible for what. And when you look at the lists of things that we want to respond to, this is still an ongoing kind of design thing. We will not approach our client within some distance, some number of kilometers yet to be determined, until we have coordinated communications between the two operations centers. When we get very close, we want them to passivate their attitude control system. We do not want it maintaining active attitude control while we attempt to grab it. That's a recipe for things falling off spacecraft. So there is an amount of coordination that's required in the operations phase, and like most spacecraft design programs, we're dealing with operations last. I hate that, but that's just kind of what you have to do in terms of budget and efficiency and that sort of thing. But we'll get there. So this was a 2010 demonstration. I wish I had the video, but it's hard to pass these things back and forth. At the Naval Research Lab of an automated repair. Let me take you through it. Up here at the top, you can see a Marmon ring. This is a mock-up of a spacecraft. This ring would have held the satellite on the booster until it reached a certain stage in the launch, and then it's released. And on the side of the mock-up spacecraft, we have a solar panel, and it is simulated to be stuck. It is Velcro, actually. And this demonstration was to drive a tool in between the satellite bus and the solar panel to apply that pound or two of force to actually, it's a simulated anomaly repair situation. Now, I told you before that what we wanted to do before we do anything like this is to dock. We want to take the dynamics out of the situation. We want to go from a dynamic to a static situation. This particular demonstration was not done that way. This was done as a free-floating dynamic repair. So the position is being maintained by LiDAR sensors on the simulated robot servicer over here. And we're using the second arm as an off-angle viewer to make sure that things are going well. This could be necessary sometime if, for example, the thing that needed to be repaired was so far away from the Marmon ring or whatever the booster attach feature was that we just couldn't reach it. So you might have to do it dynamically. Not the preferred option, but this demonstration showed that is at least feasible in some cases. So if this were a video, you would see, we have another sensor here. It's a little laser. You kind of see a red line right there. That was looking for this gap because the line turns black in the gap, and that's what the target of the tool was to go in there. So if this were a video, you would have seen that solar panel pop out when the force was applied. So a very comprehensive and convincing demonstration that these repair things are pretty feasible. I said we wanted to attach things to satellites, so the Air Force is interested in attaching, let's say, cameras so they can look around their satellites. NOAA is interested in sending up some meteorological sensors this way. There are entrepreneurs that are thinking about sending up sensors for agricultural purposes to go to GEO. GEO is a great place because you're always staring at the same thing. And if you can do this, you can now think of sending up payloads that didn't have to be integrated with a bus. So much less expensive and faster to integrate, as long as you can get them there and as long as you can prove compatibility with the host spacecraft. So EMI and center of gravity offset and all that sort of thing have to be worked out. The question is, how do you get them there? How do you get these payloads to GEO if they don't have a bus? Well, one way to do it is to share some room on a satellite that's going to GEO anyway. So you've probably heard of hosted payloads. This happens to be a hosted payload that is detachable. So there is a set of springs, basically, this lower object, gray object, is a set of springs that remains on a commercial communications satellite. They have extra room and they have extra mass because they had satellite designs that used old-style batteries, but when they converted to lithium-ion batteries, they got some benefit out of that. So they're trying to sell that benefit in hosted payloads, and including this concept, this DARPA concept, which is going to fly, I think, in January or February on a commercial satellite called PODS, Payload Orbital Delivery System, but it's mounted in the battery bay of a commercial satellite, and then these springs actually ejected out into space. It could be just a free-flying satellite with some communications or whatever, or it could be something that's intended to be installed on another satellite. So in this case, here you can see a little ball and spring sticking down, ball and stick on a spring, sticking down from the bottom of the strongback. And that's a special feature that we have a tool on the robotic servicer to capture. And we can take this and transport it anywhere around the GeoArc we want to go, and either unpack it, take things off of it, or install it whole as is. And there'd have to be some sort of a tool to place it on its new host spacecraft. We have already done 2 such tools. One of them is kind of like a vice grip, and the other is actually a hot glue sort of thing. So if we add together this ability to do installation and replenishment with the delivery capability, now we're talking actual on-orbit logistics. FedEx plus the cable guy, right? And PODS is certainly not the only way of getting things to GEO. We have the ESPA rings. You could have a dedicated payload that was full of things that you wanted to install around the GEO belt, and then RSGS can come and capture the payloads however they come up, transport them, unpack them, and install them on today's satellite. So I may not have emphasized enough the fact that our objective here is to service today's satellites, those that have been in no way prepared to be serviced. And usually the first question I get from an educated audience like this is, well, what are you doing about standards? Well, you see, to service unprepared satellites, there are no standards. We assume that if this all works, right, that the community will suddenly go, hey, we need some standards, and that'll start happening. But right now, they're not necessary for any of our functions. Actually, when I talked about the difficulty of refueling and all the steps that are involved in that, that's a demonstration that standards are really necessary. We've identified at least 30 different configurations of fill and drain valves for propellant. And our tools have to accommodate all of those. So that's really nasty. And it's something that we hope someday is taken care of with standards. But standards for modules, standards for refueling probe configurations. Gas stations would be a lot less nice if you had to have 6 different nozzles and figure you had to know which one went into your car and that sort of thing. So we assume that will be fixed someday. Now, I want you to know that all this robotic servicing stuff is not just DARPA fairy dust, okay? That other people are serious about this. So SSL, our commercial partner, as it turns out, but this is a NASA project, is looking at the possibility of putting a robotic arm on their commercial communications satellites, not to service other satellites, but to do things actually on their own satellite. So today, these large reflectors, I showed you a picture earlier of the New Dawn satellite, had a couple of reflectors on the side. Each one of those has a deployment mechanism, motors and structures and hinges and that sort of thing. They're heavy and they're expensive. What if instead you had a single robotic arm and its job was just to take reflectors off the launch locks, put them in plugs? It not only saves costs and weight, but it turns out that you can add more reflectors. Customers like that. So this is not just an experiment. This is something that has real appeal to real satellite customers. So here's a design of a satellite that normally has 4 reflectors, but now it's able to have 6 because of the presence of this robotic arm, which has reduced cost and reduced weight. It did start off as a DARPA seedling, very small one, but now it is going forward under NASA tipping point program. And imagine now that the synergy between servicing satellites that can move things around in GEO and satellites with robot arms on them. So imagine further if the satellite had the equivalent of a USB port on it, where you can bring up new electronics and that sort of thing. Yes? Yes. They were, and they will be the first time. However, there's no reason they have to be, right? So the commercial industry has a problem right now. The commercial communication satellite industry in GEO has a problem. They're very happy that the manufacturers are building satellites that last 15 years. But their customer bases on the ground change every 5 to 7 years. So if you're stuck with what you launched with, you wind up with a white elephant. You have to figure out somebody else you can sell that satellite to. And because these antenna patterns are very custom, they're very bespoke for whatever the customer base they're servicing. They have many, many, many little spot beams and that sort of thing. But if you take the South America one and you move it over to Africa, it may not do a very good job servicing your customers. So imagine if you could, and all those patterns are determined by the reflectors. So imagine if you could bring new reflectors up and replace them, and the presence of this arm would make that, I won't say trivial, but it would at least make it feasible. So launching reflectors later is a very appealing thing. But that arm could also be used to attach, let's say, a new electronics module to an equivalent of a USB port that was on there as well. And that electronics module was produced later. Now, can we play this? That's the big question. It's only 30 seconds long, it's no great loss. But it actually shows the ground demo of that arm, that robotic dragonfly arm, picking up a reflector and moving it. Do we know if this is feasible?
We can try it.
Yep.
Yes, okay. So there's the end effector. You can see the gripper there is really a cylinder, and it's gone out and it's picked up a reflector. Oh, that was it. Thank you. You can do it again. You can do it a second time if you wouldn't mind.
We have the technology.
I thought I had a 30-second version. This is an 11-second version. But this is being done with NASA funding under their tipping point program, and it's complementary to what we're doing in the DARPA program. And by the way, NASA Goddard also has a robotic servicing program. I kind of failed to mention that. It's called Restore-L. Uses the same robot arm that DARPA is using. That was the one that was developed 2005 to 2008. But now you can start to see that people are getting more serious about this space robotics stuff. So why, right? I think I've harped on the why long enough. DARPA is helping to get this stuff up there quickly. Somebody, a couple weeks ago, I was actually at a NASA workshop on using in-space robotics for future astrophysics missions, and I'll talk about that in a little bit here. Okay, maybe 5 minutes, Michelle, is that all right? They said, well, this doesn't really seem DARPA hard. And the first thing I said was, well, I take that as a compliment because we've been working on it for 15 years, so we've gotten it to the point where it's not DARPA hard, that's great. But we say, sometimes DARPA invests not because it's DARPA hard, because it's DARPA necessary. We just need to see things move in a new direction, and this is like that. We are investing in making this a sustained capability, so we'll have enough propellant and enough electronics reliability and that kind of thing to make sure we can do dozens of operations over several years. And by being able to add things in GEO, we want to lower the cost of access, right? If you don't have to integrate your payload, whatever it is, whether it's a meteorological payload or a space weather sensing payload or whatever, you don't have to integrate that with a bus. It should be faster to build, cheaper to build. And we want to start thinking about assembly. We want to start thinking about building things out there, whether they're telescopes or radio antennas or structures where you can hook multiple payloads or whatever, RSGS will actually represent a laboratory where between its servicing missions, you could send up assembly experiments and validate your on-orbit assembly concepts. NASA could do it, commercial communications industry could do it, the military could do it. And so the hope is that things keep moving and more capabilities are established in GEO. We have invested, DARPA has invested in some modular sub-satellite capabilities. It's called Satlets. The company that's produced them is NovaWorks out in California. These are single degree of freedom reaction wheels that are also energy storage, propellant, and computing and communications, and they can be snapped together seriously like Legos. Seriously like Legos. That's maybe another piece of the puzzle about how we do things. Down in the lower right-hand corner is an image from NASA of a telescope assembly concept that they had been working on for several years. You can imagine the same sort of thing being used as a huge communications aperture to look down from GEO. And someday maybe this logistics stuff, particularly the delivery of propellant, won't be as complex as it is today. So that's our vision. And I told the industry, I said, hey, this is like a newborn baby. You have to feed it. You have to take care of it. It's an industry that doesn't exist yet. We need to work together to share our insights, to share our discoveries, to share our lessons learned, to make this all work, because it's better for everybody. I'm hoping that, and DARPA will probably sponsor some conferences in this area in order to facilitate this information sharing. I do believe that we're not out of ideas here. We're as a matter of fact, so many keep coming up at every conference like this that I go to that I'm very encouraged that there's a sort of a mental stimulation that this concept of on-orbit robotics and complex operations fosters. So I look forward to your questions, and I thank you very much, and I thank the organizers for having me.
So any questions?
Yes. Right over here, please.
No, okay. Don't know that I need that, but I'll go with it.
Well, they're online as well. So.
Thank you. Good point. Eric Andrews at Goddard Space Flight Center. You've called out in this presentation specifically a GEO feature, and as you pointed out right near the end of your talk, there's a LEO capability, Restore-L, that they're working on at Goddard. And you can envision something that's even beyond GEO, out at L2 or something down the road. Can you comment a little bit on whether this is an artificial breakout, or is there something that specifically has driven you to GEO, or is it just a handshake with others that they'll get another piece of the pie and this is yours? If you'd comment on that.
Right, I understand the question perfectly. And I would rephrase it as, why are we going to GEO specifically? Why do we choose that? There is an economic motivation to go there for our commercial partner. By doing multiple missions around the GEO belt, they're sustaining their business. It's a militarily valuable orbit. The top two military satellites, the advanced EHF and the space-based infrared system, are stationed there, so there's a military driver. And of course, it has this feature that all of the customers are on a single ring, so the amount of propellant that it takes you to get from customer to customer is very small. So that's why we believe we can do dozens of missions. LEO is harder because the orbits are very scattered. You can imagine someday, if people start looking at this, you can imagine preferred GEO orbits. If you go in this GEO orbit, you'll be able to be serviced. There is a servicer in this orbit, where if you choose some other orbit, sorry, it's too hard. It's going to take 1.2 kilometers a second of delta V to get over there, and we're just not going to spend that on you, right? So that's the way I see it moving. It's not so much that it will only ever do it in GEO, but there's a certain operational change that would have to occur to make it feasible in GEO. In terms of L2 and cislunar, is another orbit. You know, if we have a deep space gateway out there and we don't have a robotic servicer next to it, that's crazy, right? Because you send things up, and you don't want to have to put RPO sensors and software on every one of the things you send up. You want to have something there that's the catcher's mitt that goes and grabs it and takes it over. So there are a lot of places where this would be valuable. There are operational considerations that made GEO the logical choice for the first one. Did that?
Yeah, Ronnie Kilo, Southwest
Then you,
Research.
and then you.
So have you guys looked at, I'm sure you have, the different types of failures that have occurred and sort of been those, and what types of failures are reasonable to be able to be serviced by a technology such as this, and which ones are perhaps out of reach, or at least for some time?
Absolutely. Of the types of failures that occur, we can help with very few. We can help with deployment anomalies and propulsion anomalies. That's about it, right? Internal electronics failures, sorry, I don't know what to do for you. I mean, someday, if you make your processor an on-orbit replaceable unit, you know, or some of your TWTs or whatever that are on-orbit replaceable, then I can help you. But the way that things are built today that are so highly integrated, it's only the things that we can do externally are the things that we're going for.
Yeah, so I would think that deployables and propulsion are probably some of the more common failures, I would guess. I don't know if that's true from your studies.
So 5 deployment failures in the last 10 years, so every other year. But the dollar value, you know, very high. Yes, sir.
This is Michael Aguilar from the NESC. I'm looking at your, in essence, business plan. You've got a number of satellites that probably have been defunct for some time, and the ownership might even be a question. I would think that you would have to have a clear ownership and knowledge in the success of the repair, meaning that they ran out of fuel, you just have to fuel them, they were working before they ran out of fuel, that kind of a thing. Secondly, there's a lot of interest in CubeSats in this audience, and I would think with the mass of this vehicle going out to inspect, that's a lot of fuel, where it might be really something that could be supported by a smaller vehicle that would go out and do the inspection for you to make sure that it was going to be worth your while to go out and service that vehicle. I
understand both your questions. In terms of the business case, down at the end here, the strong business case is for pre-planned refueling at about the midpoint in a spacecraft's life. So SSL already has a contract with SES, the world's largest GEO operator, to refuel one of their birds after we get up there. So the desire, the business case for that is strong, but it is the pre-planned one. It's not, oh my God, it's going to go away in 3 weeks if we don't, you know. There is a requirement by the International Telecommunications Union that you super sync your GeoBirds. You don't leave them there to die. Sometimes they die, and that's a shame, but the requirement is to get rid of them. Now, in terms of the smaller satellite, I completely agree with you, right? I have to spend, you know, let's say 20 kilograms of propellant just moving around to inspect somebody. If I had somebody else that could spend 1 kilogram to do that same inspection, that would be great. I only have so much funding. So, you know, there's a certain amount of miracles we're going to do, but not all of them. But that's certainly one that people have suggested. They've even suggested having it tethered so you can kind of bring it back. Unfortunately, the tether dynamics there make that a little weird. But yes, sir.
Hi, Chris Landauer, the Aerospace Corporation. Talk about integration. Some of these add-on boxes are going to leave you with hardware that isn't fully integrated, in the sense that pieces are working more or less independently. We're going to need a whole new style of software integration to run those things.
Job security.
I want to write a program and go away from it. Just a point that is going to be of interest to everybody here sooner or later.
Right, especially when you put the equivalent of a USB port on the outside of the spacecraft. By the way, that USB port's already been developed. I need something to hold the tools on the outside of our servicer. That tool holder also has power and data feed through. No. It's a launch lock, but it's also reusable. But it also has power and data feed throughs, because some of the tools need heat, and some of them are active. They have circuits in them, so we have to do it. So that same object, that same tool holder, could be integrated into another, a new design spacecraft and provide you a priori the ability to attach new things. And then you would need the software support for that, absolutely. There's a backup question, a follow-up question.
I, as a software guy, was appalled to learn how much software there is in the ball bearings. And clearly, there's going to be software in everything. So that's part of my issue here.
So we think, yes, and we think we're flying on the servicer about 700,000 lines of code. When you look at that stack that I had for the, but there's also the payload mission manager. There's the FDIR and all those kind of things, the RPOs. So there's a lot of stuff going to fly. At that Italian conference that I went to on communications satellites, I learned about the payloads for these new high throughput satellites. The processor to do all the beam steering and everything, the one design that I saw had 128 connectors and consumed 5 kilowatts of power. So engineering, both the processors and the software is getting much more complex as time goes by. Yes, sir.
What's the approximate cost of the spacecraft and the launch?
The question for those of you that couldn't hear it was, what is the approximate cost of the spacecraft and the launch? DARPA doesn't usually comment on its budgets, and I won't. And I also, the amount that the commercial partner is investing, since they're bringing that bus on their own nickel, that's a proprietary number. But a typical commercial geocommunications satellite is around $300 million. This will be considerably more than that.
What are the launches going to cost?
Yeah, and because this one's going to bring a lot of propellant for sale, it's going to be even more massive than a typical one. Upwards of 7,000 kilograms, actually way upwards, if, depending on most optimistic. So we'd like to launch on a Falcon Heavy, or maybe an Atlas V 551 or something like that. We have to do a lot of our own orbit raising because the spacecraft is so massive, so we will have electric propulsion in addition to chemical, because that's just much more efficient, but it's not timely. So there's still trades going on that.
Yeah, hi, Brian Rishikoff at Odyssey Space Research in Houston. So we work a lot in rendezvous prox ops for human spaceflight, which has a lot of redundancy and reliability requirements. And clearly that's for human life, and I'm sort of interested in the reliability and redundancy requirements associated with this because of the potential for debris and other complications if things go awry.
Absolutely. So we'll fly 2 narrow field of view cameras and 2 LiDARs, so those are both redundant. We obviously aren't going to approach if we don't have operating sensors. We simply are out of the game if that happens. In terms of the software, so we have 2 robotics processing modules. I guess I can't really get into the details of what's inside those, but they're much more powerful than a typical flight computer because of all this stuff they've got to do. Cold spare, but we have the ability to, and obviously now some of the stuff that we're doing for reliability and prevention of collision has to do with automated actions. Right? If there's unanticipated motions or that sort of thing, both the arm and the bus will be able to do automated withdrawals. And of course, one of the reasons that I think SSL picked Draper to do the RPO is their work on Cygnus. So they have the human spaceflight rendezvous and prox ops experience. Yes? Way back. Oh, you have a microphone. Okay.
Yeah, Ziv Eckerling, the Aerospace Corporation. The previous speaker mentioned debris.
A lot of you guys here.
Yeah. The previous speaker mentioned debris. Have you looked at this as a platform for active debris mitigation?
In one sense, yes. In another sense, no. So NRL did a spectral survey of objects in the graveyard, a light curve analysis to see what their tumble rates were. And we could dock with 90% of them, roughly. There's about 10% that have angle rates that we don't like. The question would be, given that my particular spacecraft is going to be a commercial entity, who will pay them to do anything about moving debris, right? So does it have the capability to do that? Sure. I will also point out there are policy challenges there. You have to have the launching nation's permission. You have to have the owner's permission. You have to. I mean, so moving debris. The program previous to mine was looking at taking dead satellites and harvesting components off of them to reuse them, sort of as a demo of these robotic capabilities. The policy challenges to that are I mean, we have a few. That would have more. So debris is a really funny thing because of the Outer Space Treaty of 1967. I mean, that's really where those policy problems originate, because it's very ambiguous. Because it was written at a time when only nation states were doing space and launching and that sort of thing. So from a technical point of view, it's feasible much of the time. From an economic point of view, it's not clear. And from a policy point of view, there's a lot of work to be done.
Thank you very much, Dr. Ross.
My pleasure. Thanks for having me.